So I want to, so as we were stating here, this is a wonderfully eclectic conference. The talks have spanned almost everything from the largest scales in the universe. We will be getting some of the smallest scales. Yesterday, Anka finished off the afternoon telling us about robotics and human-robot interactions. Part of it was dealing with autonomous driving. Jane is going to tell us today, I would say the view is more from 30,000 feet, and how we understand traffic and its impacts, and being able to deal with that mobility. Jane and I are currently in a battle between the Department of Energy, LA Metro, organizing them to try to get them to work together, providing free resources to solve some of these problems that we hopefully will hear about today. So,
Thank you. Well, good morning, everyone. I do know it's not July 30th, 2017, so I apologize for that. I used an old template for my slides. What I'm going to talk about today is a myriad of things. I'm going to talk about transportation and the transformation that's going on in transportation. I'm going to talk about the data that we use in transportation, which includes geospatial temporal data as well as maps. And I'm going to just throw out some of the really interesting challenges of working in this space for you to think about. So we're all quite aware that we're going through a significant transformation, which is why half of the room is not here. It's because we have learned that we don't need to be in the same room anymore. And what's happening is it's really changing how we think about the world and how we interact in the world. And so what we have is all these computational tools that are generating representations of our world and the like. And we are getting big data on it, which allows us to model and predict. We've got the Internet of Things happening, which is generating all kinds of interesting geospatial data. And the networks are getting tremendously more capable. I used to work for OnStar. In the year 2000, I was the director of technology. And we couldn't get any of that data out of the car because there was no bandwidth. The first OnStar vehicles had analog phones in them, analog radios in them. So look at what has changed in just this period of time. So we have a convergence of IoT, bandwidth, and data science all coming together, which is really exciting and really challenging and also very costly. So there's a lot of interesting aspects to what's going on right now. And this transformation is, some people saying, are fundamentally changing the way we live, work, and relate to each other. And we need to take note. So citizens and social systems are now interacting through technology. So there's this convergence happening. So what I'm going to talk about is mobility, the movement of people and goods. So we know this is true, but in 1 minute, this is the kind of information that's moving now. So we've got Google searches, which is capturing where we're wanting to go. It tells us a lot about human beings and what we're doing, which is one of the challenges in transportation, because we have data about how many people are on the road, but we don't have much data about why they're on the road. So there's that kind of pesky human problem in the midst of all this data, is that those pesky humans are very chaotic, and we don't know why they're there and what they're doing. It's kind of amazing when you look at Amazon is selling $265,000 worth of goods every minute. And that's probably low now. That's probably an old number, which is fundamentally changing our logistics systems, which I'll talk about later. So it's unfortunate you can't see this. These are beautiful images. You should see them on my Retina screen. These are images of geospatial data. So this came from data that we worked with when I worked at HERE Technologies. HERE Technologies is a mapping company. And they collect all this data by virtue of delivering traffic products so that they can tell us what it looks like out there on the road. So they're really rich images. They look much better on those screens if you look at those screens. They're just beautiful. They tell us about the structure of the city. They tell us about where the hot spots are, and lots of interesting information buried in their cell phone traces. These are just cell phone traces, but here collects them from fleets and the like. So go ahead.
What are the colors?
The colors, oh, so forgive me. This is a data science group. Blue is fast speed, red is slow speed. So they're colored by speed.
The speed of vehicle?
Of
Your cell phone moving?
Of those devices that are moving. They're just devices. So I don't know what kind of device it is in this picture, but we can separate it out. Yes, right. So what we're getting just massive amounts of geospatial temporal data via smartphones, vehicles, IoT devices, and then we are also getting LiDAR images, LiDAR and images. These are the things that are being composed today to make the next generation maps, so high definition maps. So maps are now changing from that 2D kind of flat map that we used to unfold in our car for people my age. Younger people don't do that anymore. But they're changing. They're changing into high definition maps that are centimeter level accuracy. And the reason why they're changing is because the autonomous vehicle folks are asking for that level of accuracy for localizing vehicles. So we get all that data, and then we have the challenge of mapping it to our known representation of the world. So I have to take the GPS data, and what you see here are a GPS data from a vehicle that we have, we had at Here Technologies that has an IMU on it. So we know exactly where that vehicle is. That vehicle is instrumented such that we couldn't even take that vehicle to China because it could be taken apart and turned into a missile, right? So, and then here is data.
What is an IMU?
Inertial measurement unit. So
No,
exact.
the International Mathematical Union.
No, no, it's an exact location. And GPS has maybe a 10-meter resolution, right? So if you take, we had a cell phone in the vehicle as well, and then what you have to do is you take that GPS data and you try to match it to the real world so that you can know where this vehicle was, that phone was. And you can see doing great right here, and all of a sudden it jumps over here based on the algorithm that we had. And then it figures it out and it says, oh no, I'm not on that road, I'm on this road, and it jumps right back. It gets very confused. So just the map matching part can be quite a challenge.
I know exactly where that is. I've been stuck there many times.
I'm sure you have in today's traffic environment. And as I said, we've got devices out there picking up data like every second. Do we really need data every second? So there's a lot of work to be done in compression, intelligent compression. So this is a representation of a part of Oakland, near where I live. And I took that data and I said, you know what? Shannon's theory, if you're folks that are information people, says that you don't need to sample that often. So you can use actually the representation of the map to reduce your sampling period. So then you can start looking at different areas and saying, if I were as a fleet manager, I can reduce the data that I have to bring in by understanding where I am on a map. So there's a lot we can do to reduce this data that we're collecting, which costs money to collect, archive, and process. So we need to start thinking more that more data is not better. Information is better, which I'm preaching to the choir here. This is an example of a city in the Netherlands called Eindhoven, where we took this kind of data, and we look to see where people are lingering. So if you've got all this GPS trails, you can start finding the hotspots of the city. Where do people go to have coffee? Where do they go to have dinner? When do they go there? So you can start to learn the dynamics of the city. But there's all kinds of interesting difficulties with this data, and it's not going to get better with IoT. Because when I'm dealing with that data, I don't know where this data came from. I don't know anything about the device that I got it from. Might be a vehicle, might be a cell phone. If you ask a carrier what cell phones are generating this data, they have no idea. So the characteristics of the device itself have to be included in your understanding of the data. Now what we would do is we would source data from all different kinds of places, all different kinds of fleets, phones, navigation devices, all kinds of devices. And this is the kind of thing you might find in it. So this is one source out of hundreds. So this is a big data veracity problem. So buried in that massive data that we're collecting is this, where we've got little collections of data bunched up here for no apparent reason. Have no idea why that's the way it is. And have no idea what to do with it. Do you throw it out? Do you use it? Here's another example. One of the sources decided to map match it for us. Very kind of them, but I don't know what map they matched it to. So now their source of data is a questionable source of data. Here's another one. They dropped a bit on the GPS data and gridded it for us. Thank you very much, but we didn't want that. Here's a really interesting one in Russia. If you were working in here with a data set in here, you'd have no idea that this is just wrong. Something is very wrong here. Here's a really interesting one where they actually displaced the data to the wrong part of the globe, right? So here are 3 different providers of data. Again, amongst 200 or 300 or how many we have in this location. And this, whoops, there we go. This is probably good data, just put in the wrong place in the world. They flipped a bit somewhere. The red data looks kind of right, but no, it's got these straight lines in it. And then the green data is just junk. All buried in to massive amounts of data. That's one of our challenges, I think, as we go forward with any geospatial data analytics, is understanding your data and the veracity. So, what this really boils down to is, and I think going forward of how we're going to operate, is we're moving into geospatially distributed temporal data analytics. That's our future. We can't do this all in one cloud. We can't throw it all up to the top and do some global analytics. We're going to start doing analytics at various levels in the ecosystem. So we'll have IoT devices doing data analytics. We'll have vehicles doing data analytics. We'll have networks, towers doing data analytics. We'll have cloud doing data analytics. So that is, I believe, where we're heading with this kind of data analytics. I just want to share with you some of the other pieces that's interesting about mapping and geospatial data collection, because these maps are going to have a huge part of the autonomous vehicle.
So when you say data analytics, what is it that you want to do with these?
I want to understand mobility. I want to understand where people are hanging out.
Okay,
I want to understand, how to manage traffic in a city.
Okay, so where are people going? Why are they there?
How do we do better logistics?
How do we get them there better, faster?
Faster.
Okay.
And this is a really key problem because our cities are urbanizing right now, and anybody who lives in the city here knows how bad the traffic is now. And it wasn't that way 10 years ago. It's really changing. And they say, I think the cost, we in the United States have the 3 out of the top 5 congested cities, we have 3 of them. And the cost to the cities across those three is like $62 billion in productivity cost, in cost of gasoline, and cost of, there's a variety of different costs that build up. This is a serious problem for our economy. And it's only going to get worse if we don't deal with it now. And that's the second part of my talk, is to talk about the transportation issue. The first part was just to give you a sense of what kind of data we're using to understand transportation and to drive some of the things that we're speaking about, like autonomous vehicles and autonomous shuttles and things like that. So this is the data piece, and then I'll tell you more about the transportation side.
One aspect of provenance of data is basically ownership of data.
Huge problem.
And particularly when the objects that are being represented are public objects, like the public roadways and the image tunnel that you might get from driving on a quote public road.
Right.
And we see it pop up with privacy issues in those imageries.
Yep.
That imagery that sometimes interferes with street addresses.
Absolutely, and then it's both sides of that. Is it interferes with the street address, but then there's people that don't want their street address in a map.
Right.
In Germany, that's huge. The map companies actually have to allow people to come in and take their house out of the map.
So there's sort of proprietary interest that's been invading what heretofore had been maybe a scientific or a municipal.
Correct, which is a huge problem. And that's kind of the second piece, is that who owns the data, right? Because most of the data that I'm showing you isn't public. It's here owns that data. Google owns their data. Apple owns their data. But we actually should own our data. That's a whole other topic.
Maybe connected to that, is it safe to assume that in these kind of horror stories of data, not provenance really, that there's no way to give feedback to the providers to say, can you do better?
It's very difficult. It's very difficult because you have to do all the work to dig it out, right? So I think there's a whole lot of work to be done on the data veracity side, because we get excited about collecting all this data, and we get giddy with the thought of what we have, and then you have to really make some sense out of it. And it goes a little bit too far over the edge, particularly with the machine learning craze, where everybody feels like you just pour all the data into the bucket and magic happens in there and poof, none of this matters anymore, right? Which I will say blatantly, that is not true. My mantra with my research group was know your data. You have to know your data before you do anything with it. And visualization becomes a key part of that, which is why we were creating all those beautiful images. Collection vehicles are out there pulling in images to find those street addresses and the like. We're all, by the way, helping them figure out what the numbers are by filling out your CAPTCHA when you get when you log into Google or whatever. But here's some example of some of the image analytics from real world. Is that underexposed, overexposed. This is Whoops! I keep hitting the wrong button here. This is photogrammetry data, so airplanes flying with cameras, where if they fly at the wrong time of day, the shadows make it very hard to classify what the image is telling you. And here's the same even just on a building. If you want to retexturize the side of a building, a 3D building that you're putting on a map, that can be very confusing for the analytics. LiDAR, I mentioned, this is another big craze right now that lets you pull out building facades, curbs, lanes, traffic signs, because it's just basically LiDAR reflecting. Luckily, our streets have reflective materials on them, but it's huge amounts of data because it's just a point cloud. It's centimeter accuracy, but it's just a point cloud, which means you have to do lots of analytics to pull out those features in that massive point cloud. And here's an example of a LiDAR trip. And so we're trying to figure out where the lanes are. So we were doing, this is when I worked at here, a lot of work to try to take all those pesky trees out of there and all that noise out of there in order to find the flat surfaces and then to look for the lane markings so that we could understand where the lanes are so that we can build that high definition map that the autonomous vehicles are working off of. So lots of challenges, and then you go into like the dead space inside the intersection where you have no help on where the lanes are as you make the turns, which can be quite complex to figure out in large intersections. So that's the data piece. The challenges, which I'm sure you all are seeing, we have a lack of labeled data sets out there for anybody who wants to do some of the machine learning associated with this. We have lack of big data for researchers. So we have this membrane between public and private where researchers aren't getting this huge data sets that they can work on. So that's actually one of my charters in the next few years is to make that membrane more porous so that industry will let loose some of that data so that we can get, you know, the research side moving up a little in the data analytics opportunity side. Otherwise, we're going to lose all the researchers into the Facebooks and Googles of the world. Privacy, as I mentioned, huge problem. Who owns the data? Actually, I should own my own data. That's the way it used to work in vehicles, but now we are all quick to say, I agree, okay. And all of a sudden, all our data has gone away. So everybody's collecting it from you, and which is fair if it's a value add, if it's a win-win for both sides. But it would be nice if we could offer our data out, things like that. We need to come up with new ways of moving the data from these devices into places where we can all operate on the data. Go ahead.
So I was at my university and had this long discussion about data privacy, and one of the things that sort of struck me was that even if so the Strava heat map release that happened several weeks ago, so you know, even though I may not feel any particular need to keep private where I go jogging and cycling, and you know, none of you may feel particularly, you know, like it's okay, you know, that you know, you're concerned about the privacy. It's like it's the aggregate of the data, and that is actually something that the current, you know, sort of technical definitions of privacy, they don't really address.
Right.
I mean, you know, privacy is always aimed at, well, you know, you have a personal need, desire to keep your data private, but in fact you may not, and none of us may, but in the aggregate it leaks.
Yes.
And the technical stuff doesn't address that yet.
No, not at all.
So maybe with, as well as mutual information, there's mutual privacy.
Yeah, or somehow aggregate privacy, you know, and I haven't seen anything that addresses that. I thought the Strava thing was fascinating.
Yes, that was a big hole in their security.
But it was one that individual people could not have done anything about. They could have acted in such a way.
Well, this is an interesting conversation, which I think we should continue, because I think it was the organization's fault in that case.
Strava's.
Right. So I mean, if you're a security officer, you know, if you're the CSO of whatever armed forces that was, you say you won't wear those devices. And that was just a hole in their awareness, I think.
Okay. Yeah.
Right?
Yeah, I mean, it's a sort of an armed forces organizational problem.
Right.
But it's not a personal problem.
No, it's not
and
a personal problem.
It's not a personal privacy problem either.
Correct.
To your point, though, you know, people may feel differently about this, and that's fine. You know, as individuals, maybe what we're missing collectively is the value of the data, right? If people are not recognizing that in aggregate the data has financial value,
Yeah.
right?
Yeah.
Then they're not starting the transaction in the right place.
And I would say that there's an interesting cultural issue going on right now, is that when you get to the private side, everybody thinks their data is worth, it's gold, right? It's absolute gold. But I keep telling everybody, it's not gold. It actually costs you a lot of money to keep it, and it costs you a lot of mining to make it worth the gold. So you really only have a few nuggets in there. So you really should work with other people to help you get the nuggets out, and then we'd all be happy.
Oh,
And-
I was very much suggesting that,
Yeah. Yes.
if people could come together to recognize how to
Exactly.
monetize their data, then they could do that for civic or whatever.
Right, which is again why I'm kind of on this, I don't know, I'm trying to get awareness across private that we need to break that barrier down, particularly when it comes to transportation, because transportation is a public concern. It's not a private concern. That's one of the reasons why I left here, is because I can't solve transportation from a product perspective. We have to solve this from the top down. And it's going to have a huge impact on our economy if we don't go after this. So this is the transportation piece of the discussion. We used to think, you know, Japan, they're all stuck in their subways, and, you know, we expect that there. This is my ride to San Francisco on BART recently, right? And you'll note that he does not look very happy. And neither was I, by the way. And this was after I let 2 trains go by. So I couldn't even squeeze my body in there, or was not willing to squeeze my body in. So it's happening, and it's happening in all our big cities. We can't build these like they have in China. There's no room in our cities to build these. And the Federal Highway says in 2035, approximately 40% of the roadways will approach or exceed capacity. So we are in a serious transformation in transportation. And by the way, transportation is kind of the unloved stepchild when it comes to technology, right? A lot of the technology on our roadways is not very new, and it's actually not very sophisticated. I could tell you stories. So again, what's key about this is it affects everybody in this room, and it affects every business, because it's not just commute. Oh, I keep doing that, sorry. It's not just commutes. It's freight delivery. It's supply chain. It's product to customer. It's retention of employees. It's productivity of employees. It's a huge problem. And again, I think the answer is going to be geospatially distributed computing. Because of the size of the data that's being collected, we can't just push it all up. We're going to have to really think about how we do this. The vision, everything's connected, everything's, you know, high tech, everything's going to be all right. But it's not that way now. It absolutely is not that way now. And what's happening in these ports is the ports used to take the containers off the ships, and they'd put them on a rail car, and off they would go to the warehouse that's located somewhere. But now, because we want our bottle of Tide soap on our doorstep the day after we ordered it, or maybe even now 2 hours after we ordered it, what's happening is they're springing up all these little mini warehouses, which means these containers in the shipyard now have to be broken down into bits and pieces, and they have to be put on single owner, small run trucks. That's hugely different than going onto a rail car to someplace in some city. So they're going through a transformation inside just the ports. That just gives you an example of a little tiny piece of what's happening out there.
So sort of looking backwards in history, I mean, the container-based freight delivery, that sort of post-war phenomenon, really worked its own revolution. And could you see this as well as a continuation?
Yep. This is forcing all the IT systems to have to morph. It's causing cities to get backed up with semis sitting in lines to get in there because they can't move the containers around. So yes, they're going to have to completely reinvent themselves as a result of what these pesky humans are doing. right? You talked about autonomous vehicles. I am on the not so excited about autonomous vehicle side, so I'll just say that straight up. I used to work for OnStar. I care about safety. I'm very concerned about safety. There's the belief that we're just going to get all this information from the transportation system, from these vehicles, and pop it up to the cloud, and we'll all know everything that's going on right now. And that's just not feasible, not yet. So are they going to grow the chaos or calm the dynamics? They could do both. We can squish more cars on those freeways. Actually, there's really interesting control theory work that shows that you can throw a autonomous vehicle into a traffic jam and it will calm all the dynamics that happens in traffic jams. So they actually can add value. But how do we use them? And what can we do with them? Because it's a very highly semantic contextual environment that we're operating in inside that vehicle. The new vehicles are very excellent at localization. They're, when I worked at OnStar, I was allowed to put a $125 unit inside the vehicle. That's all I had. Now we've got Volvos that have cameras completely surrounding the vehicle. They've got LiDAR. They've got amazing sensors in them today. So there's a lot you can do from a localization point inside the vehicle. This is, I wanted to show you an example of a good use of automation. This is actually my advisor at the University of Minnesota, where they are using high accuracy GPS systems to instrument highways in Alaska, so that when they have big snow events, the drivers of the snowplows can drive the snowplows without visual feedback. So they've got radar, they've got high accuracy GPS. This is an excellent example of a good use of automated vehicles. And they're using them today. This is actually a Caltrans video, where Caltrans is using it. So this is really exciting. Now, whether I think it's good on the campus road out here, that's a different story. The vehicle is not a consumer device. And we have to remember that, because we tend to throw consumer devices into vehicles and think that we can manage a vehicle the same way we can manage a consumer device. Vehicles are deadly weapons. And we have to be very considerate about how we put technology in these vehicles. So again, on this story is when we drive, we made a lot of judgments, we make a lot of predictions, we process scenes. And if you, unfortunately, I had the Department of Energy in yesterday, so I didn't get to see the talk. There's a lot of really interesting work being done in scene analytics. But we're not there yet. We're not there yet. And it's a very complex stochastic environment. This is not an air traffic control system. This is not airplanes. This is very different. So this is an example of the high definition maps that these autonomous vehicles are using. So that all that LiDAR is shown right here, all those lane markings. That's the product of that data analytics that I was showing you earlier, collected by vehicles like this, the Google vehicles that are out there. And note that Waymo was out in the snow trying to figure out whether their autonomous vehicle can operate in the snow, because these sensors all have edges of technology in them. And so they didn't know how to do that. So they went out there and started trying to learn. So that's where we are in the real world of autonomous vehicles. You get past the hype that's in the literature. There's a lot we can learn. This is an example of some connected vehicle, effort that was at, I think it was DOT was running in Michigan, where they're collecting CAN bus sensor data off the vehicle. So we can learn a lot about where people brake, that can inform how we want these autonomous vehicles to work, to operate. You can see where people are slowing down here. This is speed again, sorry for my original lack of explanation. So you can see kind of where people tend to start to slow down to allow other vehicles onto the road. You can get a lot of information out of it for sure to understand how to build autonomous vehicles better. This is an example of we were looking at what is a good speed to go around this curve. So we took a bunch of data of taxis going around that curve, and we found that even though you might be able to go through that curve faster in your vehicle, there's a G-force that we as human beings feel fairly comfortable with. So everybody kind of went to that same speed as they went through the curve. So that tells us a lot about how we operate on the highways, and we can maybe build vehicles that kind of operate more like that we would be comfortable in. And this was just an example of how, if you just have the windshield wipers, you can start to localize storms, because the vehicles are all telling you that there's a storm going on, and you could easily, if you had connected vehicles, you can communicate back to a path behind you to let people know time to slow down because there is a nasty storm. So regardless of my concerns, the world is moving forward. And the autonomous vehicle activity is well on its way and will happen. And already people are starting to propose expressways that might just be autonomous vehicles only. Nobody really knows what the answer is right now for this. But what I wanted to kind of put in the back of your mind is, for those of you that are aware of the Tesla crash that happened in Florida a few years ago, that was an edge of technology problem. It was a white truck against a very bright sky, and he shouldn't have been driving the vehicle as if it was an autonomous vehicle. Teslas are not autonomous, they just assist. And he just went right underneath the truck and died. This is now, there's more coming, is that a Tesla just ran into the back of a fire truck on a freeway at 65 miles an hour. They survived, which is a testimony to how safe the car is. But we're hitting the edges of the technology already. So what will all this technology do? We have no idea what the impact is going to be on energy, on emissions, we just don't know. And we're learning now, and we need help. We need all of your help to think about these things. We've got rideshare coming into cities, Uber, Lyfts, that are dramatically changing the traffic profiles. I think a year ago we had 45,000 Uber, Lyft drivers registered in the city of San Francisco. And if you walk down the if you walk down the streets, you will see Uber, Lyft, Uber, Lyft, Uber, Lyft. A lot of them with just one person in it, which means they're driving around. So that's a huge issue. Then we've got, of course, the third dimension happening. I don't know if you know, but in Dubai, they're already putting in air taxis, station to station, one-person air taxis. So we are going into the third dimension. And, of course, we can always go to the underground, which is also an option and popular with Mr. Musk. So why do we care about this? Because we care that we're building urban environments that people want to live in. And if we don't address this problem, we may have cities that nobody enjoys living in. And our emissions will go up, and we won't enjoy what the outcome is. So we need to start looking at efficiencies at vehicle level, system infrastructure, looking at demand. Why are there so many people out there? Our vehicle miles traveled were 3.2 trillion miles in year 2017, which is the 5th year of increase. Now the gas prices are down, which is part of the reason, but we're just driving more, we're just out more. Our populations are higher, we're urbanizing. It's all happening. So what we need to do, this is the project I'm working on currently, which is a high-performance computing project. We need to understand urban at scale. Nobody can do this right now. Nobody has the data, and the models sometimes take days to run, depending on what you're trying to model. So city planners are working with models that take days to run. And state-of-the-art models maybe take hours to run. So this is the work we're doing up at Lawrence Berkeley Labs, is to try to do urban scale modeling. So one of the things is we don't have a lot of data, so I'm working with industry to get that probe data so that we can understand more about what the dynamics look like. We need to build models for the veracity. Veracity, you've seen, can be a problem, and then fusion of multiple data sources, because the reality is those sensors that are out there on the roadways, they only work part-time. Somebody comes on and does maintenance and they mess it up, or they put things on the wrong side of the road. All of that happens. It's real world data. We need to reduce the data with intelligent compression algorithms, which I talked about earlier. We are oversampling the world right now. And we need to build high-performance computing modeling if we're going to get at urban scale dynamics. When I said you can't do this from a product-based perspective, this is an example. I always tell the people that are working on the ramp metering systems, I say, who do you think is controlling all those vehicles out on your freeways? And they say, well, I've got my ramp meters, right? And I say, no, Google's driving all that traffic. Apple's driving all that traffic. Here's driving all that traffic. And they're all taking different samples of data because they're using the devices that they have out there to make decisions about where they want to send their people. And they are all using different routing algorithms. So this is really a non-cooperative gaming problem. Alex is going to talk about this more in the next session. Alex and I work very closely together. So we don't have any control about what's going on in the freeways right now because they're doing it all. They have all the data. So what we're trying to do is build this high-performance computing solution. I clearly have too many slides, so I'm going to go really quickly now. We're going to have to learn the patterns out there. We're going to have to understand what the drivers of those patterns are. And we're going to have to start thinking about control ideas on how to move people off those freeways, how to route them better, how to get people not showing up on the freeways. There's a whole lot of work that needs to be done. So we're working on a project that's taking real-world data that's coming from a connected corridor down in Los Angeles. And I'll show you what that looks like. We're going to put it into high-performance computational tools for modeling the urban scale. So this is the connected corridor I'm speaking of. So this is the corridor of I-210 in Los Angeles. It goes across 3 cities. So we've got 3 cities engaged in managing this. We've got street lights. We've got inductive loops that are giving us flow information. We've got ramp meters. We've got all kinds of things. And then we have, again, those navigation systems that are moving everything around as well. And this corridor has like 5 incidents a day. Not good drivers in this part of Los Angeles, I guess. So the question is, how do you start to manage this? If you have an incident, what do you do? Where do you move all these people? And if you have 2 connected corridors, then what do you do? If you move them in the wrong direction, they'll mess up the other corridor. So how do we deal with this problem? So this is this is the classic traffic assignment problem. Alex will talk about this in a minute. But basically, you have a model of your network, your road network. You are assigning vehicles to their routes on that road network. You get a cost, and you sum up the cost. That's the traffic assignment piece. And then you put a solver in the midst and try to figure out where to put them. So that's the Nash equilibrium solution. Alex will talk about that in a minute, as I mentioned. What we're doing is we are putting in trip legs of vehicles going different places during the day, routing algorithms, and what the routing algorithm penetration might be to kind of model how those navigation systems work, and then create network disturbance in order to come out with emergent behavior and try to understand better what's going on the highways. So this is a project that we call Mobility, and we're trying to leverage the supercomputing assets up at Lawrence Berkeley Lab. I'm going to go quickly through this. We're taking advantage of a lot of the work that's been done already. We took a simulation of finite element analysis and repurposed it for traffic, which is pretty cool. So now it's an actor-based representation. A link on the road network is the actor, and the vehicles travel along the link. And they congest according to a classic traffic equation that represents as I get more vehicles on my link, then I slow down. So that's how congestion is represented. And the link mediates the congestion. The challenge is the reason why those modeling systems work so slowly is because a lot of them use what we call a conservative parallel discrete event simulation, where there is a master of the universe for the simulation. Everybody calculates where they're going to go. The shortest distance, everybody goes kerchunk, and then they do it again. So that doesn't lend itself at all to high performance computing. You need distributed mechanisms, and which we call the optimistic parallel discrete event simulation. And how you partition your network is key to how well this works. And luckily I have one of the masters of the universe doing that now. And so we are working on a San Francisco Bay Area model. The road network itself has 1.1 million nodes with 2.2 million links. So a piece of road is a link and 2 nodes. That's the road network. So that the whole Bay Area, 9 county, is 1.1 million nodes. Our initial testing, we can run 3.7 million vehicles in their daily path, going from home to work, to lunch, to work, to home, all different kinds of patterns there. We can run 3.7 million agents, which turns into 9.5 million leg trips and 2.4 billion vehicle arrival events. We can run that in a minute. So we've gone from days, hours, to minutes on the compute facilities at LBL, which means we can now start to really look at what congestion means in a full urban scale environment. So these are the top 10,000 congested links in the Bay Area, and it's showing how this is kind of a delay view of the problem. So you can start to see where things tend to build up as the day goes on. This is noon time, and then you'll see the congestion come back up when everybody's on their way home. Then, now, since we've got the dynamics, then we can start doing some work on it. This is literally hot off the press. We just did this. So we've got a long way to go yet. Flow is the vehicles per minute. Where are all the vehicles building up? So the last view was congestion. Where are you getting delayed? It's a function of the capacity of the road. And now we've got an insight into where all the flows are happening during the day. So we're capturing the dynamics of the entire Bay Area in a minute. So there you see 3 o'clock, Bay Bridge starts to build up again. 4 o'clock, it gets worse. It's hard to see because there's red links buried underneath here. It's colored again. Red is slow, blue is fast. But this is the top 10,000 out of a million. So then you can start looking at trip counts from a location. You can start looking at distance from a location, and then map it into fuel consumption. And then you can learn more about what's the impact on the energy profile of the Bay Area. And this is kind of a trip lag example for a 1 kilometer region during that day. So you can start to see these trips building up with the distance of those trips via the routing algorithm I showed on the earlier slide. So then you can start seeing what the pressure is on this network.
So, Jane, I guess at the end of the day, what are you looking at optimizing?
How do we get people to their destination faster?
Okay, so not necessarily, say, total fuel consumption in the future.
Oh, that's very important. No, it's
Oh, okay,
it's
so-
productivity, it's energy,
Okay.
and it's there's 3 of them: product, energy, and those are the 2 that I care about, right? And that's what business cares about: productivity. You don't want your employees sitting on this mess out here, right? So, and we can't. You know, all your delivery trucks that are trying to bring you your Tide soap on your front doorstep are sitting in this as well. So logistics people care.
Throughput, fuel consumption, and something else. When you talk about like standard network routing, you know, there's throughput, congestion,
Yep.
I guess fuel consumption is one.
Yep. But DOE very much cares about how much fuel we are using.
I guess coming from Europe, it's astonishing how many things you can get delivered here.
Yes.
There's a lot of people that really want to bring you stuff.
Yeah.
So are you also trying to congregate these people so that they have a more optimized way of doing so? Because of course, if there's one person bringing you a soap tablet, to
Well, you know,
so that there's something that the private could also do on themselves, federate or something.
absolutely. But right now they're not. They don't want to because that's their edge. So eventually we're already having the problem that all the boxes that Amazon delivers in can't go through the landfills, right? Because there's so much cardboard going through the recycling system now.
Amazon is actually doing something slightly differently. They're centralizing some of this delivery stuff. They have these lockers at Whole Foods.
Yeah.
Right.
You can get stuff.
But it's
They're
very,
trying-
very small scale.
Yeah, I mean, but
Yeah.
it's really, and this is just the last couple months.
But there could be all kinds of things that we could do. There are so many creative things that we could do to solve this. So I could offer to pick up your groceries when I'm there. You've sent in your delivery and I'm going there anyway, and you live next door. You know, there's all kinds of things we could do.
I could just be patient and go on Saturday.
Well, you could, but we aren't.
So I guess from a transportation simulation, a vehicle simulation point of view, the Bay Area is blessed with a poor to crappy transit system.
Yeah.
So how do you interface, and likewise LA Basin, I guess, same.
Same.
But the developing urban areas around the world aren't
Right.
aren't
This is just the beginning.
So how do you interface this kind of a system, this kind of a simulation system with transit?
Right. Well, transit we can put on, the buses we can put on there.
Yeah. With,
Right, but I mean, it's to the next generation. We're not there yet. This is amazing that we can do this, right? And we can only do this because we are working at Lawrence Berkeley Labs.
So how would you characterize not including fixed line transit in this model with respect to your optimization goals?
There are all kinds of optimizations here, right? One is you want to take people off the roadway. Right now, we're just looking at the roadway, right? And we have to validate that with what we know about what's going on the roadway. We have to add transit buses in here. We are not yet looking at the transport of humans. We are only looking at the simulation of vehicles on the roadway right now. But this is a 3-month-old project. Got a lot to do.
I have a question back on the veracity set of issues. In those diagrams with the dots, is it ever or mostly the case that a dot is an individual device?
Yes.
Could you not then use an IMU? I mean, I have two questions, and they're both kind of in the experimental rather than the simulation side. Would it be possible to use an IMU then to particularly locate data that you could then recover from the data that the provider gives you? You could co-locate a device and an IMU, knowing that that data would go through whoever the carrier is and come back out the other side. And then you could use that to error correct.
Yes, that in fact was when I showed you the map matching part.
Oh, yeah.
That's what we were trying to do. Because that was a IMU and a cell phone in the same device.
So could you repeat that technique across carriers in order to
Yes,
improve data?
if we could get that kind of data.
But you just need an IMU and a cell phone, right?
Yeah. Yep, it sounds simple, but get that data at
Or
scale.
one per carrier.
Right,
I guess
right.
the other and possibly more questionable experimental technique would be to potentially provide an incentive in the real world, and then you'd be able to test both the modeling and potential gains. I understand in India, for instance, they do synchronized release of employees from different factories.
Yes,
Right.
yes, we should be doing that.
Well, and so with this, it seems like you could not only do it, but you might know where to do it, and then you could measure back whether or not it worked.
Right, right. But we're not doing any of that yet.
You should buy an IMU.
Yes. So I have to finish up in 2 minutes, so I'm just going to finish up. So this is an example of what the data that's being collected. This is 19 million points per day. This is part of that project that we're trying to get started. So this is for all of LA Metro. I just go really quick. One thing that we need to think about is, should we be doing, can we use technology to get people off the road? Can we send one person with some virtual glasses to do the job of 3? So we need to start rethinking how we move people around. Can we start looking at data so that people that are doing sales forecasting and the like, they don't have to go travel to everybody in the United States, where you can have meetings in virtual.
But they do have to come downstairs for talk.
Yeah. Right. So I just want to conclude here. I think that the technology is moving faster than our social systems can handle right now, or our social systems are handling right now. We need to quickly solve the increasing stress on our cities. Urbanizing is happening. We need better sophistication in our tools to control it. I haven't even talked about policy. These folks are making big decisions right now, right? The state of California has just approved driverless cars on the freeway, assuming that they have a remote control, which is really spooky, right? And here's the tweet by somebody that said, boy, now I can be stuck on the highway with a bunch of empty cars, right? So we haven't even talked about that issue, and we started to talk about this. This is a huge problem. So I'll leave you with the idea, are we thinking through the very hard questions related to the pace of the technology and the impact on our social and economic health? And for the machine learning people in the room, we have to consider how brittle the technologies are that we are deploying. So, thank you. And pitch for IEEE conference in Maui in November. We're going to have a large-scale computing for transportation studies if you're interested.
Can we attend virtually?
No, we will not show it.
So I actually have sort of a social justice question. So this is all fantastic for, fairly well-off people who can afford a Volvo with these, wonderful things, and who have jobs to, go to when they feel like it.
Yes.
But I live in Southeast Michigan, not too far from Detroit.
Yes.
Whose public transportation system sucks.
Sucks. I lived there for a year.
Sucks.
It does.
The road system sucks
Yes.
too.
Yes.
And all of this technology is fantastic to move, wealthy white people in the Bay Area from their nice jobs, but it doesn't help the people where I live.
I totally agree with you. That's why I'm saying the technology is moving way faster than the social thinking that goes with it.
I mean, if we could just improve improve the buses in Detroit, or the response time of the ambulances and the fire trucks, and turn on some streetlights in Detroit. It would be, you know,
The whole,
I'd rather have the technology do that than you know, put
Right.
cameras on my Volvo, which I can't afford.
right, and the whole autonomous story is it's gonna improve accessibility.
But it doesn't.
But it doesn't. You know,
It doesn't
the Uber
help
and
me where
Lyft
I
drivers don't go to the bad neighborhoods.
Right. Yeah, it doesn't help where I live.
Yeah, and we haven't even talked about emissions in the neighborhoods that are around the concentrations of the emissions.
I,
You gotta.
I sadly think that this reminds me of the very first thing that I learned about traffic, which is they build a traffic light only after a few people die
Died.
at an intersection.
Died.
And to me, it seems like this will get an edge and will start affecting things when people complain enough, when people lose
Yes.
money, when
Or lives.
or lives.
Yes.
And that's going to take the trigger to implement these things.
Totally agree.
I just don't see it happening any other way.
And the AV people, the people who are excited about AVs say it's going to save lives because most of the fatal crashes are because of human error. But that might be true on that side. But how many accidents will be initiated or created because it's an AV? Nobody thinks about that side, what the edge of that technology is, and when will it crash? Because a remote control person sitting in a control system looking at a vehicle going 70 miles an hour is not going to be able to switch context any better than you in the driver's seat sleeping, right? This is not an air traffic control problem.
Any other questions?
Okay, cameras, that's well, with respect to about 15, 20 years ago or so, telecommuting was supposed to
Yes.
drop traffic congestion. And,
Right.
and it, maybe it made its contribution, but I'm tempted to sort of categorize it as a little bit of techno hype that's comparable to AV techno hype.
Yep.
As opposed to, say, assisted driving.
Right.
The technology.
We are in maximum hype cycle in all of this stuff right now. Maximum.
But telecommuting was supposed to solve
So,
these
I know.
So telecommuting, I have seen work well for solving problems only when there's a carrot and a stick associated with it. So at the lab, parking has always been free. They have just started discussing basically billing us $1,000 a year if you want to park your vehicle up there, because they're building new buildings and getting new parking spaces. In addition to which, they are giving you incentives to telecommute now. And that's the only way I've seen that. And so like I said before, I think it's going to be a carrot and a stick to get us to change the way we behave, because unlike Europeans, Jet Katerina, I do want to be able to say, I ran out of laundry detergent, I'd like it now, okay? And the sad fact of it might be that we are living in a momentary piece of time in which we can do that and our kids won't, you know? And that could happen.
In
Is
addition
that the
to
social justice coming back here?
in addition to the carrot and stick, yeah, incentives are really important. I think there's also just a learning curve, where people sort of imagine that they know what this technology, what its implementation is going to be. And I would offer that one way that I think, certainly around here, I don't know about in Michigan, I hope so though, are shared bikes, right? Because that is a collectively operated, transportation system. And in my neighborhood, people are getting used to the fact that there could be a random bike someplace.
Right.
You know, and I
But-
think that if we learn through
But
those things.
But again,
Look today.
yeah, it's a myriad of solutions because that doesn't solve the young mother with the 3
And
children
I'm not
problem
saying
in the
that-
bad
I'm
neighborhood.
not saying that bikes are a solution, I'm saying that.
It's a piece of the puzzle.
They can be
As the-
dismantled and sold for scrap metal.
Which is probably
What I'm trying to say is that there's a learning curve, a social
Yeah.
learning curve for this type of thing at all.
Yep.
And that shared bikes are a baby example of that, whereby people can see some of the pros and cons. And some places in the world it's commonplace already.
And that's one of the reasons I had that 3 bubbles is that we've got people, technology, and social systems. Those things are all getting integrated right now, and we're at the very first part of it. And we've got a technology curve that's going crazy.
All right, let's thank Jane again.
Thank you for listening. Appreciate it. On all the good questions. I don't see